And we are going live. Who knows if it's live? It says it's live. All right. What is up, everyone, on this beautiful Tuesday morning? Hopefully, you are having a great week so far. Uh, my name is Jason Watts. If you're not familiar with who I am a CEO and founder of a little automation company out of Alabama, which is in the southeastern United States. If you're not familiar with where that is, but yeah, so got about 20 something years of experience with Siemens automation, and we are going to be talking about some great topics today. What's up, everyone? If you are in chat when you come in, say hey. It's we usually have a great international crowd here because that's one thing I love about Siemens is that uh, it's all over the world and everybody loves it. And well, everybody, everybody that's weird like us, right? You know. But no. So as you're coming in, say hey in chat as we're getting started today. It's been a little while since we've had a live stream, and sorry if there's noise in the background behind my definitely brick wall. Definitely not a sheet with bricks printed on it. I've got my 3D printers printing out some stuff for a project that we're doing that's starting up. So, what's up? What's up, Michael? What's up, everyone? Um, yeah, so I've been told that you can only hear the 3D printer going when I'm talking. And I realize on this that's pretty much going to be the entire time. Yeah. So if that's a little annoying, apologize, but it's progress. It's coolness. I might I might show you what it's printing out later, but because it's actually part of something that we're going to be talking about today. So one of the things that we love to do on this stream is to talk about drive topics, right? Because I started off my career working on Siemens master drives and spent about, I don't know, a little over 8 years as a Siemens drives and motion specialist at a Siemens distributor. So I was the kind of tech guy that you would call in the South, in the Alabama region. And yeah, so I love my drives. And we've got a topic that we're talking about today that has come up a couple of times. I've talked about like load sharing and some of the ways to kind of synchronize different axes and different projects, and it keeps coming up of like how to do this specific type of thing, and it's a winder application. We've talked about things like with during DCCs. We talked about it. A lot of the videos that are on my channel are based on winder applications. So if you go through and look at the actual edited videos, there'll be a lot of like how to use MC Home, MC Move, or Move Velocity, MC Move Absolute. Like all of those are actually on a winder that my company, Alpha Industrial Technologies, our team designed and implemented at a roofing plant down in kind of in Alabama. if if we're kind of out of the Tuscaloosa area, Roll Tide, and most people on the planet don't know where that is. Most people in the U.S. don't know where that is, and where we where this plant is that we put this winder in is even in a more remote and obscure location in the middle of nowhere, Alabama. So, but it's really cool. And I've got a couple of videos. I think I have like a short that's up there of it kind of just the rolls winding up and kicking off and kind of the whole process. We're really proud of the way that winder turned out. Our mechanical designers did a really great job on that, and yeah, the controls are pretty fun. And one of the things that I realized is that application, that winder application, kind of touches on a lot of different things in industry and in kind of motion. And there's a lot of different winders out there, and it could kind of be a little intimidating if you've ever worked with one. It seems like there's a lot going on, and there kind of is, but it really boils down to a couple of things, and we're going to talk about. Going to start from the beginning, start from kind of the concepts like what's in a winder, what type of winders there are, what are some of the physics and kind of the things that you're having to overcome on a winder, and yeah, go from there. Hopefully by the end of the stream, we will have a project that is kind of fleshed out in a way that um, has kind of the core structure of how to run a basic winder, and so yeah. So if you're joining in for the first time, thank you for coming, and thank you for taking a part in this live stream. I try to do them every week. I had some stuff going on last week that prevented me from doing one last week, and I'm actually, shocker, don't tell anybody, but I'm going on vacation. It's this thing to where you go somewhere and then you don't do anything. And it's so weird for us automation engineers. It's crazy, but I'm actually going to be doing that later this week and into next week. So this stream, what's up, T-Ferg? Yeah, so this is going to be maybe a little bit longer stream to make up for the difference between the fact that I won't be able to stream for probably about 2 weeks or so. Will be the next stream. But yeah, so without further ado, let's get started talking about these winders. And if you have any questions, throw them in the chat. I can see them out of the corner of my eye most of the time, and I'll try to answer them in good time. But yeah, we're talking about winders today. So let's go through and start from the sketch pad. And you can see my little marks over here that tell me don't draw up there. And by the way, if my face covers up something important like on screen, yell at me in chat and just just tell me that I'm covering up, because I would go back through and be like checking through my videos and I realize I'm like talking about something that's behind my face on these screens. So be sure if I'm doing that to yell at me in chat. Yeah, so what we are talking about today after coffee is we are talking about ooh, need a brush, not a selection tool. We're talking about industrial winders. And tell you what, I'm gonna throw this on. I'm gonna put a little bit of music on. If the music is too loud, please let me know. I'm working. Sometimes it seems like you can't hear it on the stream, and then sometimes it's like louder than my voice. So I'm gonna throw some music on, and we're gonna be talking about industrial winders. Let's get this going. All right. As always, the music for the stream is brought to you by my brother-in-law, Andrew Nelson. He puts together beats. They're pretty fun. But as always, yeah, shout out to him. So we're talking about industrial winders. If you're not familiar with what an industrial winder is, you've never seen one, look at the thumbnail on this stream, because that actually is a picture of the roofing winder that we built last year and installed, and has been running and doing pretty good. We're still tuning in the full line, because we did the entirely new upgrade for the line, and there were some things that we're still working through to get up to full speed, but the winder is smoking. But yeah, so check out the thumbnail if you've never seen it. We'll talk about what that is. So like in the thumbnail, you kind of see in the front, you have this bar that goes across it, and then kind of a little bit further back, you have this, what's called the knife. That bar in the front is called the mandrel, and the thing that's kind of in the back next that you see is the knife, and that's actually what cuts the product. And then you'll see the little yellow roll behind it. Those are what we're going to be calling the metering rolls. And so from a side view, that looks like we have our mandrel, we have a knife, and this is kind of in the vertical position, and then we have what we call the metering rolls. And before we get too deep into it, this type of winder is what is called a center wound, wound, center wound winder. It's kind of difficult to say. And that just means that um, we'll use this little guy here, that when you feed in your material, it builds up from the center. So the actual driving force is on the center shaft. And so in this case, it would be this mandrel. And so as this spins around, this builds up, gets bigger and bigger and bigger, and your product keeps going in either on the top or on the bottom, depending on what. But center wound winder is wound from the center. Ooh, it's crazy. I know. Groundbreaking. The other type of winder that is possible is a surface wound. And its objective is to put the torque instead of in the middle. So you still have a shaft where your product kind of builds up, but it has a second roll that's here, that this is where your torque is actually applied. So you have to kind of press these two. There has to be some sort of like pushing force right here in order to force everything together. And your product comes over like this, and this little small roll sits there and forces and kind of spins. So this would spin this way in this case. Actually, nope, it would spin this way, the other way. So that this one, you would want it to spin like this, and so this would spin in the opposite direction. So it would look like that. So, but there's a reason for either one of them. If you're wanting kind of the simplest version of this is, I mean, there's pluses and minuses to each, but just know that the roofing winder that I'll be talking about today is this center wound winder. And so you still have to deal with a couple of different things. When we start talking about the physics of these, I will kind of tell you that how this surface wound winder solves some of the problems that come up. But most of the time, what you see are these center wound winders. You can have kind of like paper products like roofing felt or printing paper or kind of tissue paper, toilet paper, whatever, like that's a flat sheet. You can have a wire or some sort of thread that is being laid out, but they're all being done from the center. Even like coils of steel, those are all center wound. They're driven from the center, and the thing that is actually turning is pulling at the same time, pulling the material on top of it. So that's a center wound winder. Most of everything that you've got will fall under this kind of designation of what this winder is. So we're going to be talking about that. I'm going to clear this out, and we're going to go back to describing this roofing winder that we have down in Alabama that has these three points. You have your mandrel that we talked about, and I'll write them out. So if you can't understand the redneck accent, this is what I'm saying. So there's a mandrel, a knife, and then a metering roll. And if you're not familiar with kind of what metering means, it's like you're measuring. And so it's another way that you could think about this is the measuring roll, because one of the things that the two things I guess that we are wanting to worry about is, like on any product, most of the time you are trying to roll out a certain number of meters or feet or some sort of like 1,000-foot roll or a 10-meter roll or whatever. And so you are trying to measure out some sort of product that is on this roll. So that's the first kind of primary thing. In the roofing industry here in the US, you have 74-foot rolls, and then you have 140 or 72-foot rolls, and then 144-foot rolls in these kind of products that we're doing. And because of that, there's a little bit of tolerance in how much is on the roll, and if you have too little, then it doesn't meet spec, and then if you have too much, you're wasting money. So in general, the owners of these companies are wanting to get the minimum, put the minimum amount on the roll to meet the spec in order for profitability. And so in the US, that's 72 foot, and then for kind of basic product, and some of them are 65 feet and stuff like that. But all that to say, measuring is important, and that's what this guy, this metering roll, you can call it the measure. Yes, you are measuring roll, because we're going to measure out the distance using this roll on a center feed winder. And then the second thing that you're going to have to worry about is, so let's write this down. Number one, the length. Number two is the tension. Okay, so on a rolled product like this, especially with a center feed winder, the more resistance you have to that twisting action in the center, the tighter the wind is on that roll. So as you are kind of, as the sheet comes through here and goes on top, there's another roll down here on the bottom, like this, and these two are clamped together. And so in between here is where your tension is built up, because these two here are actually in contact. Let me go through and actually draw them like that so that it actually makes sense. Nope. Select all this, delete, and let's redraw that, because this makes a lot more sense like this. Clear this out. So we redraw this, and so we have our paper that comes through and is clamped down between these two rolls, and it goes and it gets start to get wound up. Well, in between here is our tension, and so this can be kind of loose back here, kind of doesn't really matter, but we want, as we are rolling this up, we're wanting that to be like tightly wound. Because if you've ever like tried to, I don't know, rewind like wrapping paper, like Christmas wrapping paper or whatever, and it ends up being this big fat thing where as it fit into this tiny little wrap, that's because when you're wrapping it, you're not putting the correct amount of tension on it. Well, obviously, if you've ever tried to do that, the reason that you don't put a lot of tension on it is because you're probably going to tear it. If you put too much tension on it, it's going to rip, and then you're going to waste paper. And so you're trying to find this balance between having a good, tight, neat roll and tearing. So in a center feed winder, the tightness, this tension that we're talking about here, is based on the torque, QUE, torque of the mandrel. So the mandrel torque is how tight you're going to be wrapping this on and how much tension is in this sheet. Very important. Like, if, just like I said, you would not buy a wrapping paper roll that was like massive, huge, and wrinkled up and all that stuff. You want a nice tight roll, but you also don't want one that's broken all over the place. So that's the thing about a center feed, is it's based on the torque. Now we talked about the surface feed a little bit. That tension, that tightness of the sheet and kind of the compactness of the roll is based on the two rolls that you have. And remember, you have that other roll that they have to kind of be squished together, and then as this one gets bigger, this one's like tensioned onto it. So you have to have kind of an extra force to drive that roll into the side of the roll in order to make sure that there's nice, good, tight wrap. So that tension, the tightness of the wrap is based on that. So that surface feed would be if you are having your product can't take a lot of tension itself. That would be where you would want a surface fed type winder setup. So we're going to talk about how to control that tension and go from kind of there. And then the third option here is, swap back over. Our third kind of thing that we're having to deal with on these winders is cutting. And obviously length and cutting have a lot to do with the same, like they're very closely tied together, because where you cut is what the length on the roll is going to be. And that sounds kind of obvious, but it's kind of a little difficult to kind of think about the first time you're going through it, of like how you need to set up when to cut. Also, depending on your material, there's a couple different ways that you may have to cut it. So this material here with this knife, in our roofing winder, we have what is called a rotary knife. So it just has a blade on one of the sides, as shown here. It has a blade, and there'll be a roll underneath here called the anvil roll. And this knife just spins in a circle. And whenever this blade here makes contact with the anvil, you can kind of see it like this. It comes by and pushes up against that anvil. And so whatever's in there is going to be cut right through there. And it's based on pressure. And sometimes that's, like some products, that's okay, but there are some issues that come kind of like into question of like, can the product handle that? Sometimes it's more of a tearing force. So it comes in, puts pressure, and then this kind of like pulls it apart. And for a lot of products, if you kind of notch it, make a little notch in it, and then rip, it's fine, because that's kind of what this is doing. But there are some products that can't handle that. They can't handle that pulling and tearing action. And so they will use what's called a straight cut knife. And you actually stop, clamp down on the material, and then, or a cross cut knife, and then it crosses across. And you either have a little like roller blade, like rolling blade, like a wrapping paper kind of like roll cutter, and it just goes across and cuts. And yeah, it has that. Or you can have a guillotine set up to where it's similar to a rotary knife, but it eliminates that tearing action, and so you'll have kind of a guillotine. Viva la revolution. And it just goes down and cuts your paper or whatever it is. Clean cut. So that's the three things that you have to worry about. Today, what we are going to mainly talk about, because the most difficult portion of this is this tension. And this is, if you can figure out how to do tension in a winder, you're going to be able to do tension control in a lot of other applications. And tension control here, while measuring your length and how to cut products, are very specific on what product you are using. Tension control, there's only a couple ways to do it, and those couple ways can be applied into many different applications. So we've talked about on another live stream about load sharing, and it's actually tension control and load sharing are very similar, and you're going to see that in this stream. We're going to go through and do a lot of the same things that we did in our load sharing live stream, but we're going to talk about how they apply to tension control. So we're going to talk about three things, or just kind of a general review. We're doing a center wound winder, and then we are mainly going to be talking about how to set it up for tension control, or that critical, how to get that tight wind and how to get to not break the sheet, because there's, as we go through it, we'll talk about some of the issues. If you don't have good tension control, you can see spikes in the tension, and you can accidentally break the sheet. So first thing I want to talk about a little bit, we're going to clear this up a little, is I'm going to go and say, we're going to go through select. Nope, I got to do this. I got to do this. I'm going to do select. I'm going to clear all this out. And we're going to go back here because we are about to talk about a little bit of the length considerations, because it's kind of interesting. There's an interesting thing that comes up when we're doing it. Coffee break first, though. As always, if this is the first time that you've either watched live or on demand, consider subscribing to the channel. If at least, like, if you're here live right now, hit the like and get the YouTube algorithm going and getting it out there, because we're gonna be here for a couple hours talking, and so maybe we can get to people that maybe wouldn't see it normally just because of your like. Because the biggest part of growing this community and getting all this information out there are you guys that are here on the streams and joining in on the VODs, dropping comments, dropping chats. So you're the reason that this is growing. The content kind of speaks for itself, and I don't feel like I'm really saying anything new. But the community that we're building here is amazing and awesome. And so, yeah, if you want to join in, definitely hit that subscribe. And the next time we go live, you'll get one of those notifications and you can maybe join us in live. So let's talk a little bit about what's going on with the length in all winders. So one of the things about winding anything is the length of how you calculate it kind of changes. And this may not be intuitive at first, but if you are taking and putting material onto an object, and it is a circular object, and any winding application is going to end up to be circular. It's going to either be like tissue paper or some sort of like flat paper product, or it can be like a wire to where you're having to kind of stack and do a thimble type of guide back and forth. But ultimately, when you look at it from the side, it's gonna be a circle. It's gonna be a circle. And the thing about it is, as you wind, the more you wind, the bigger that circle gets. It's always going to expand out the more you wind. And you're like, okay, cool, whatever. That's no big deal, duh. The problem is when you go to measure the length, you might sit there and say, okay, I've got an axis right here that has a nice, wonderful encoder on it. And you're like, okay, I've spent the money on this encoder on my mandrel axis. Good job. And so now you're like, well, I'll just take and do the circumference of it, and then kind of do a little bit of math and get my length away from that, right? Well, the problem is what your sheet sees and what the mandrel sees is constantly changing. Every time, especially in a like a paper product, to where you're constantly laying on top of it, it starts out this big, which means, so 2 pi diameter, 2 times your diameter times pi, is going to be the the circumference, right? So, and that's how you're going to get the length, because the length around this circle is the circumference. And so you'd say, okay, circumference times rotations equals your length, right? Well, your circumference is constantly changing because it starts out, your circumference is based off of this diameter, and then as it grows, it's based off this diameter, then it's based off this diameter, then it's based off this diameter. So you can see that the diameter is constantly growing. And so your circumference is constantly getting larger as you go. And so it's not quite as simple as being circumference times the number of revolutions, which it is. So circumference times, we'll say revolutions, like in revolutions, the number of revolutions. Well, this part here is constantly changing. And so that is the problem with measuring length in a center feed application, and really any application. And so there's 2 ways to go about it. Okay, you can use what's called a diameter calculation, and we've talked about these on other streams, to where we've seen there's a couple of toolboxes that have diameter calculations, and a lot of the stuff that goes into it is parameters like the thickness of the material. There's called a lay ratio, like how many rotations before it goes up to the next level. That would be like in a bobbin application, or like a wire draw or something, to where you're winding up and you're having to kind of go back and forth with a wire. That would be like a lay ratio. So how many rotations is it before it bumps up and starts going back, and bumps up and starts going back? So then there's a compressibility, because we talked about this before. Some materials might be really, their thickness is really defined, like a piece of metal. Well, saturated felt, for example, so the way that you make roofing felt is you take paper and you saturate it with tar, amongst other things, but you saturate it. And depending on how spongy that is, how thick your material is, it can be vary slightly. And when you're saying, hey, I've got, say, a 1 millimeter thick, and then you could vary up to like 2 millimeters. So it could be plus or minus 2 millimeters. So what do you say? Do you say, obviously it's not gonna be negative, but a minimum of 1 up to 3 millimeters thick on this paper? And you sit there and you say, okay, well, that doesn't seem like that's a big deal. It's only a couple millimeters. Well, over the course of a lot of rolls, if you aren't compensating for that, you're going to lose a lot of money, or you're not going to roll out enough material, because you think that your thickness, so in that case, you would end up wasting money, because your circumference would be bigger than you are assuming it is. And so for every rotation, you think it's only moving, say, half a meter, and it's actually moving 0.6 meters. And so you're giving up that 10 centimeters every rotation in kind of the extreme. And so you're just giving away product for free. So obviously you don't want to do that, because we're about making money, right? Well, that would be what's called the compressibility. And so the problem with compressibility is it changes depending on how much tension it's under. So if you're wrapping that really tight, it's going to be really compressed. If you are not wrapping it really tight and it's a compressible material, then it's going to be loose, and it's going to be like not as compressed. So every layer is going to give you a bigger impact in your circumference. It's a lot to keep up with. I mean, and it may be that if you have an incompressible material like a steel roll or something, a diameter calculation is okay, as long as you keep good tension on it and it lays, like, makes full contact around it, you're good. A diameter calculation's fine. Well, we talked about this before at the beginning of using that measuring roll, and that is where you come in and say, all right, I don't really care about the diameter of the mandrel or the wind. I'm going to take a place that I am going to measure out how much material is getting sent into this kind of like end of the machine. And so in this type of setup, we still have the paper coming in here, and in ours we use the encoder from that the metering roll, the measuring roll, because you got to have something sitting there making tension. And so yeah, you could pull straight off of, like, if you had like an unwinder sort of set up here, you could absolutely pull straight off of another roll, okay? But you would have to figure out some way to set up some sort of tension arrangement, right? Well, in ours, we do away with this, and we have our just kind of like black box back here, and our product comes from it. And then we have these two metering rolls that clamp down hard, and we use the encoder signal off of this in order to actually measure out the length, because you know, hey, I've had this much product run off between the metering roll. And so pretty straightforward. And then so you kind of get to solve two issues with one axis there. You get a good accurate measurement of the length. Asterisk. I'll talk about some problems with this. You get an easy measurement of the length because you don't care how big this diameter is. I keep drawing the radius and calling it diameter, but yeah, so there. You've got a good accurate, because you don't care about the roll, you just care about how much product has gone past the measuring point. And so that's that. So the problem is, what if this pulls too hard and it slips right here? And so it kind of slips past, and you kind of get a, well, that metering roll isn't going to account for that slippage. Okay, so a couple of things that you can do. You can use like a sticky roll. So like these rolls are coated in some way to make them have better friction so it doesn't slip, which that's what we do in our winders. We have a urethane coated roll, and if you look at the thumbnail for this stream, you can see that the yellow on that back roll is actually like a urethane coating, and so it kind of is a spongy to be able to connect and create better tension. Whereas a lot of the other rolls, you don't want friction, and so those are just steel rolls. Well, you could do that, or you can eliminate the slippage possibility by taking and looking and putting a really high accurate laser that is looking down at this, and that kind of looks like, all right, whatever. So it's shooting a laser down and actually measuring the distance, just like your mouse, right? So the little laser underneath the mouse, it's doing the same thing. This solution, you're going to have a metering roll there, okay? So you kind of have to have that no matter what. This laser, in the US, these lasers are about $10,000 or more. 13 sometimes, like depending on what they are. But these industrial environment lasers are quite expensive. But when you start talking about what the product is, and how much. Remember, we were giving away without having an accurate measurement. You give away material. One way or another, you end up losing money every roll because of either slippage or something that you can't compensate for. This laser compensates for it. It says, hey, I don't care about sheet. I'm looking at the actual sheet, and this is how much sheet is on this roll. And so that we put one of these on, we have put some of these on some of our systems that we have worked on, these winder applications. And even in the $10,000-$13,000 range, price range for this, they'll pay for themselves in less than a year, just because you don't think about, all right, I'm saving 4 inches of my product on a sheet. Okay, well, if that product is, you're making $100 a roll on it, you can see that over the course of a year, you don't have to save, or you don't have to save many rolls in order to pay for that laser. So again, going back to production, like stuff that seems really expensive actually pays off in the end. And so you buy this $10,000-$13,000 laser, and then in the course of a year, all of a sudden you're making more money. And so it's very tough if you're dealing with to where you don't have upfront money. And so I get it. Like sometimes you just don't have the money up front to be able to put onto this technology. But there's pain up front and then prosper at the end. And some managers, some companies can understand that, and a lot of like smaller home, like family companies have a little bit harder time because that money is coming straight out of it. And yes, and it's sticking sharks with laser beams. And so yes, sorry. I had a comment for those that you're watching on demand and you don't have your chat watching. I have someone that's just talking about laser beams. But yeah, so very expensive lasers, but they're super cool and they can pay for themselves really quick. All that, we use this metering roll, and we won't really talk about the metering roll when we set up here in kind of when we start setting up our project. We probably will set up an axis for a metering roll, but we won't really talk about it very much because it's pretty basic. We'll talk about like its purpose is in the program. You are going to set your move. So if you want to wind a, let's say 30 meter, I don't know, I think I have more US people on this chat. So approximately 90 feet, whatever that is. But if you're trying to wind out like a 30 meter roll, what the position profile will look like it will start out at 0, and you're trying to get up to 30 meters. And so it'll sit there for a second, and then you'll start the move, and it'll move up to 30, and it'll look like that, right? And if you looked at this from a speed perspective, it would be sitting at 0 speed. It would accelerate up. It would wind for a little bit, go down, and be back at 0 speed, right? So those are the two different kind of position and speed functions. And you would be looking at this from the perspective of this roll, the metering roll. And I know I circled 2 rolls there, but we're going to call that 1 roll. So you would look at that from the perspective of the metering roll, because everything else, length doesn't really matter to the mandrel. It really just cares about torque, right? So the position, you would set up a position move to run like an absolute, well, maybe not an absolute. We would want to do a relative from this point up to 30 meters. So we're going to do like a relative 30-meter move on the mandrel. I'll show you how to kind of set that up. Man, wow. That's rough. Hey, effing chat for my spelling skills. So we would do it, and it's not even the mandrel. How did it catch that? You know, it's not the mandrel. We're doing a 30-meter move on the metering roll. Okay, so, and then the mandrel is just going to, and I'll show you how to set this up. We're going to set it up in tension control. Once it gets pop, set up into tension, then we start this 30-meter move, and there you go. You're good to go. You have 30 meters. We'll worry about cutting later because, yeah. So that's how you measure. You measure with a different roll most of the time than the from the center. So all of these are from, again, from the metering roll. And so this would be your wind speed. And this would be your wind distance. Okay. And I'm talking about all this because once we get into the actual programming, I'm gonna not draw all this stuff out as much, but you're still gonna need to know these terms. So if you're joining in and like on demand and you are wondering later on about some of the terms, you're gonna need to come back here. So welcome from the future. If you're coming back to this point, you just missed where I just talked about kind of the terms. But yeah, so what we're gonna do now is, now that we kind of understand what we're gonna do, we're gonna set up our mandrel into our tension control like this, and then we're gonna go through and run this move. So get our mandrel tightened up, and then we're going to move out 30 meters. That's going to be our goal. And this is the part of the equation that is really useful to know how to do. And so that's what we're really going to focus on. I've got tons of videos talking about kind of how to set this up, but we will talk about that later. So let's move over and start talking about Portal. Okay. So let me go. So if you've made it to this point, I appreciate you so much for sticking around on the stream and kind of going through. If you have questions about anything that we've talked about so far, you're here in chat, hit me up in chat. If you are watching this on demand, then yeah, feel free to ask your questions in the comments. I try to look on and keep up with all the comments, but yeah. And if you have another question, you're watching this on demand, you have a question about something completely different, go ahead and drop a comment here. I'll see it, and it might end up being the topic of next live stream. So we've got Portal, and I want you to see that other than this little library that I have open, I'm going to start a new project. And so we're just going to do a new project, and we're going to do a new project, and we're going to go and we're going to make this. Coffee break, loading. And I'll talk about this library that I got open here in a second, because first thing we're going to do is we're going to go into devices and networks. And again, I'm going to kind of blow through this. I've got a couple of different videos that show you how to set all this stuff up, but repetition is good. I've done this a couple of times just in life, maybe a couple thousand, I don't know, but I still kind of have to think about some stuff every now and then, you know? So first thing I'm going to do is I'm going to go in and I'm just going to add in a controller. And I'm going to put in a 1500 CPU. I'm going to put my trusty 1515 TF because that is alpha spec. And so alpha approved. These aren't the cheapest, but they give you the most flexibility. They're mid-range. You could do safety. You could do the technology applications. We're not going to be using the technology objects on this project. I'm going to try to make it more general because honestly, this type of project and this type of thought is really not just for Siemens. You can do this on other brand drives. You can do this on like an ABB drive. Like, I'm not as familiar with the product lines, but you can do these on Rockwell, Yaskawa, Mitsubishi. You can do these on lower tier. We're going to probably use, I don't know. I haven't quite decided yet. For those of y'all in chat, do you want me to use S120s or G120s? So y'all get the authority on what happens. If you're listening here and you want to see a G120 application, type in chat G120. If you want to see the S120, type in chat S120. And I'm just going to name this stuff. But yeah, y'all let me know what you're wanting to see. Yeah, we got an S120 already. So if you're wanting G120s, better speak up. Because everybody on this channel knows I love my S120s. Don't make me go get my shirt. I've got my S120 engineer shirt. But yeah. So I'm just naming my PLC because good Siemens programmers name all their stuff, right? And I say that because you'll see a lot of projects. I cringe. Like some of the first projects that I have that I'll like go back behind. I'm just like, oh, these aren't named. It's still PLC 1. Oh, drive 1, drive 2. Oh, so, all right. So we're gonna save this right now. And we have 1 vote so far for S120. So if you're wanting anything other than S120, you better speak up because I'm about to go over here and start dropping in an S120. So drives and starters, SINAMICS drives, we're gonna go with S120. Voting has closed, and we're gonna add in a CU 320-2PN. And so if you're not familiar with the S120 system, it is what's called a centralized kind of method. So it has a single control unit and then multiple inverter and rectifier sections. And so we are all of the brains for all of the axes, or not all of the axes, up to 6 servo or vector drives are available on this one control unit. Whereas with the G120, you have a control unit for every drive, and that's kind of common across most brands of drives, even on your servo drives. You don't have a lot of this kind of centralized architecture. So we're gonna assign this to the interface 1 of this control unit, or sorry, of the PLC. And now we're gonna go in and we're gonna add in a couple of drive. So I'm just flipping. I clicked on the object. I clicked on that control unit I just made and clicked on device view. And now if you notice, your hardware catalog has changed over a little bit. And so we're going to add in, just because we like technology here, we're going to throw in an active line module. We'll just do a book size 27 amp because this is going to be a fairly small system. What these line modules are is this is going to be a common DC bus setup. And if you're not familiar with that, it is a really powerful way of getting really good torque control, good energy efficiency, because you have one AC to DC rectifier, and it creates a DC bus. And then you have motor modules, you have inverters for every motor hanging off of that DC bus. And what this gives you, it's it's definitely not cheaper, but it gives you kind of a poor man's uh, automatic regen. Because if, like we'll see in this application, one set of stuff is always going to be breaking, like you're going to be generating tension, and so that's always going to be feeding back power. And if you don't have any sort of regen in the system, you're literally just going to have to burn that energy off, because you're going to have one that's pulling and then one that's backing off and putting negative torque into the system. So in order to do that, a common DC bus immediately, that since they're hooked up to the same DC and you're never getting that energy back to the AC, it just kind of goes whoop when the energy is breaking. Anything that's motoring, so you have generating and motoring loads. If you have a generating load, any motoring load will use that energy automatically. And it's much more efficient because you're only going through the inverter bridge and you're not having to go through a second set of IGBTs in order to get back to the grid. So you're not losing that second set of switching losses. So what you have here is a common DC bus, and this ALM is the like Ferrari, like Bugatti Koenigsegg of rectifiers, because this thing, not only does it have the ability to regen back to the line, if you have too much braking motors, it'll put all that energy back onto the line. Not only is it like that, it puts that energy back with less than 3% total harmonic distortion. So really beautiful harmonics. Puts it back by default at a unity power factor, and you can actually program it to swing a power factor, so to inject reactive current. And if you don't know what that means, like, that's okay. Like, it's a little black magic, but it's really important to power people. And if you start saying that around the right people in your plant, they'll start spending a lot of money on this stuff because of power factor correction. So this active line module has power factor correction, and not only does it correct for whatever it's like this system that we're building, it can actually set either a leading or a lagging power factor of that system. So really cool. So it can actually correct for power factor for other crap in the plant too. Third thing that this active line module does is it actually is a buck boost converter. So normally the DC link on these drives, and if you're not familiar with the way a drive works, every drive has a DC link. You have, well, every AC drive, AC to AC drive. Every drive comes in AC, converts into DC, and then chops it up into like an AC signal out to the motor. Well, in this type of system, it is actually, most systems, if your line voltage, a sectional drive, I'm not sure what that is. Barack, will you describe that, what you mean by sectional drive, as I continue, and I'll see if I can answer that. So if in a normal drive, if your input voltage starts to lower, the voltage on that DC link will automatically start to lower. So if you live in an area that doesn't have very good grid conditions, and either your voltage will start to brown out or even go high, this active line module, you set a set point for your DC link voltage. You set a DC link voltage, and this, if the input voltage starts to lower, it will correct for that by shifting and doing some black magic like we talked about. And it will shift the phasing and the firing of it in order to keep that DC link voltage up. So that means your voltage, your incoming voltage will drop, but your motors will still see that the rated voltage. And so you'll still get your rated torque. And so you won't have on your equipment, you won't have problems regulating that torque. So if you have a really sensitive system, about torque, and you don't have like the best power. So I'm from Alabama. That's a very rural part of the US, and some of the places there the power is not consistent. The voltage is will vary wildly. And so a plant in those type of places would be really good for this active line module because it has that buck boost converter. It actually sets the DC link voltage, and you can change that, and it will regulate that DC link voltage independent of the line supply. Super cool. Um, so the the that's what this active line module is. So the second thing, if we're so yeah, fill me in on kind of a description of what you mean by a sectional drive, because I'm not familiar with that terminology, and maybe I can kind of go back and explain it. But so one of the cool things about this setup with this common DC bus setup is you can take this line module and power 10, 20, 50, 100 small drives. You can have one really big section, or you can have one really big line module, and then all the motor modules are running off of that, and they're all, you kind of set up your own DC voltage grid inside your plant. So this stuff can be really cool. And these line modules, I think, go up to like 800 kW or maybe 1000 kW. Let's see. Catalog. Where is it? Selection. Let's see. How big do they go up to? All right. What? 1400 kW. So that's on 500 volt. So 480 looks like it's 900 kW for the 480 system. And I've actually helped. No, there's a. Oh, that's amped. Yeah, 900. Yeah, so I've actually installed or helped commission and set up a couple of these. I've done, I think, an 800 and a 600 before. They're big, very big. And what you could do is you could set up one of these big systems and basically power, like one of these setups that they did, they were powering a lot of rolls on at a steel mill. And so where you have your ingot going and it's getting pressed out and like stretched and lengthened, you have hundreds and hundreds of rollers that are moving this big ingot back and forth. And so that they had at one point all DC motors on all of that. Well, they went through and started converting them, and they would power this one really big active line module and power all of those motors. And then they would set the power factor for that, which is 900 kW, and they would be able to set the power factor to correct for the other line. And so they would be injecting reactive current and correcting the power factor for the other line sitting right next to it. And so just that alone, the power company was charging them like crazy rates to just because of their power factor. Just by them putting in this like multi-million-dollar system, it paid for itself within a couple months. Like, it was ridiculous to return on it. But that was really bad. So let's go back to let's see, it's related to sectional drive. Sectional drive is paper produced. Oh yeah, so this, okay. Yeah, so oh yeah, SI paper. There's a Winder process library. There is a couple of different blocks. So in chat, if you don't have chat pulled up, we have someone that's asking relating to sectional drives, and apparently I wasn't familiar with that term. And apparently it's a paper producing process, and absolutely this type of winder that we're going to be setting up, I'm using it in roofing, which is a paper product, but it's a saturated paper product. But I've also seen this same application in pulp production, so actually producing the product that gets saturated. And so yeah, this probably goes right along with this sort of stuff. And the one of the things that this is definitely not a new topic for sure. And there are a lot of toolkits and toolboxes and applications to where you can go through and use those things. Um, understanding understanding how these things work and how to set them up from scratch really sets you up to a position to where when you understand it, you're more than using a tool set. And so, and knowledge is something that no one can take away from you, because you may end up somewhere else to where you don't have access to either the Koenigsegg of drives like the S120 with an active line module. Maybe you're having to work with a lower performance drive, like maybe a G120, or even something like a V60 or a V20. You can start to do these things that we're going to be talking about in the very low end. Now, you're not going to get the performance, but because you have this knowledge that no one can take knowledge away from you, you'll be able to take that across brands, across products. And one of the things that the tension control that we're talking about in the winder, it looks like I'm going to have to start to implement this in the line, and it has nothing to do with winding, but we have a couple of rolls that are giving problems because they're not getting properly tensioned. And when they're switching products, and the tar will get hotter, and then it'll get colder, and like all of these variations, they weren't, the product quality goes out. And so you can implement these tension control techniques that we're going to be doing in other places that really will help you out, not just in winders. So yeah, C paper is definitely a cool toolkit. Out of curiosity, is that in PCS7? Is that a process library in PCS7? Or is that something that runs like in Portal, or kind of just a regular library? While you're answering that, if you're still here, Rock, I'm gonna go through and add in a couple of motor modules onto this system. But yeah, so if you could tell me if C paper is PCS7, then that would be really helpful. If you're not familiar with what PCS7 is, PCS7 is a control. Is a product that's by Siemens that it is a process control. So yeah, so what we're doing here is obviously going to be in TIA, but so that would be an application that to where if you're using something in PCS7, this is going to teach you how to kind of do those concepts that is in like these C paper, and there's winder control boxes and things, toolboxes and things, but this makes it to where you don't even have to worry about that. So I'm bringing in a couple of axes here, and I'm going to name them because we've talked about this before, and I'm doing things different ways every time just to show you the flexibility of TIA. We're going to call this one the mandrel. And we've talked about these terms. If you're coming in late or on demand, you can hop back into the beginning of this where I kind of talk about what these terms are. But the mandrel is the business end of the winder. It's what's making contact with your product. We're going to bring another one in. We're going to rename this one the metering roll. Metering roll is what measures out your product and creates tension. And we're going to select another 9 amp. Obviously, this is a pretty small setup. And then the last one that we talked about is going to be the knife. And so this is we're going to make a rotary knife setup. And And we're going to call this a 5 amp. And if you've noticed, I've been doing all of these in servo. And if you're not familiar with what the difference between servo and what this other option is, universal or vector, so most people think that servo control is for servo motors, which would most people consider permanent magnet motors. Now, with a permanent magnet motor, like a Siemens 1FK7 or 1FT7 or 1FK2, something like that, those permanent magnet motors, you have to use servo control. But you can absolutely use servo control on an induction motor. So even if you're using some like lower end motor, I say lower end, but like a Black Max, like a Baldor Black Max motor, or like a WEG inverter duty motor, those are still really good motors, but they're not permanent magnet motors. They are asynchronous induction motors. Well, you can absolutely use servo control on those motors. You just have to have an encoder on the motor to run servo control. Servo control is a control method. All it does is it says, instead of doing a calculation, a vector calculation, I'm going to look at the encoder, I'm going to look at my feedback, and that's how I'm going to close my speed loop. If my encoder says I'm running 10 RPM, I'm running 10 RPM, and that's all that matters. If there's no extra calculation. In a permanent magnet motor, that's the only way to know where the poles of that magnet actually are, is by having either a resolver or an encoder. So that's why servo control is for permanent magnet motors. Now, if you didn't know this, a 1PH8 motor, so a Siemens 1PH8 motor, is a servo motor, but it's actually a polyphase wound asynchronous servo motor. That's a lot of words. Just know that it's just a really fancy Black Max, and Siemens people don't send me hate mail on that. But it's just a really nice, specially designed asynchronous motor. And the cool thing about that 1PH8 motor is it is rated at 0 speed, full torque, just like a DC motor. So if you are looking to replace DC motors in your plant, look into the 1PH8 asynchronous motor. So we've got our axes here, and we've got them built into our project. And honestly, at this point, we can go through and set up our actual, there we go. We're gonna click here. Maybe not. And one of the things about it is, technically, since we have this active line module, we're going to use the see, this is on a 400 volt. So the active line module always has what's called an active interface module. We talked about the active line module being able to do all these cool things on the line side. Well, part of the reason why it does that without completely destroying everything connected to that system is this active interface module. So if you are going to use an active line module, you absolutely 100% have to use the active interface module. Otherwise, you will instantly blow up every capacitor on the line that's connected to this thing. Because you're taking a really powerful drive and then turning it around backwards and shooting it back into the line. And the only reason you get that like 3% total harmonic, less than 3% total harmonic distortion, is because of the active interface module. Otherwise, you're gonna have voltage peaks of up to 2000 volts on your 480 volt line. Bad day. So have to use this active interface module. So let's go through and add in the next thing that we need. We need to add our motors in, because this is where we actually add our motors. And what I'm gonna do, just to save time here, is I'm gonna drag some drive click motors in. And if you're not familiar with what drive click is, it is a proprietary communication that uses an Ethernet type cable that to go out, read the encoder, and it knows the information. A drive click motor has all of the motor information built into this drive click connection. And the first time that you start up this system, it'll go out and say, hey, what's my motor? What type of rating is it? What's my pulses? What, all of that stuff, it'll pull it back in. Otherwise, I'm going to have to go through and select like a motor data input, like an induction motor, synchronous motor, whatever, and have to put in all that data. So I'm just dragging these drive click motors in just to save time on this stream, because otherwise you just go, I'll show you real quick what it looks like for motor data input, an induction motor. Say if you had like a Black Max with an encoder or whatever, you can just pull this in and then go through on motor details, type in its nameplate data. And then if you have some of this stuff on here, then you can put that in. But yeah, and so that's that. Now, if you want to use servo control, you have to have a measuring system, right? So we talked about this before. You can use like a Black Max or a WEG motor on one of these systems and run servo control. And honestly, knife maybe might be able to work. You probably, if you're going to do one of these, an induction motor, you probably want it to be the mandrel, because it's going to be running in torque control anyway, or torque control. And so, but in this case, we're running all these in servo control. So you want to put in like an HTL, TTL encoder, and you're just going to drag that. And if you didn't notice where I pulled that from, I am kind of going a little fast. When you go to the device view and you have like the S120 C320, this whole catalog changes. You're now, instead of big system with PLCs, you're only looking at S120 components. And so I click on this object here and I just drag in my thing. I have my measuring systems, HTL, TTL encoder. I'm just going to drag it and attach it to this motor module. And that makes it to where this encoder will be associated with that motor and motor module in the program. And that's critical. You can just kind of toss one of these out. Well, maybe not here, but you can absolutely set up an external encoder with its own system that's not associated with a motor, but you don't really want to do that. Especially in this case. So here you would select, all right, I've got a 2048 HTL AB with a reset. So pretty decent. And if you notice, once I set that, I'm clicking on the different objects. Once I set that little block went dark gray. That means that it's configured. When they're light and not filled in, that means all of the data isn't filled out. And in this case, I click on it and you see that I didn't fill in my rating plate data. Okay. I'm going to undo that. That's just about that. I'm going to delete this and I'm just going to throw a drive click. I'm just going to throw this drive click motor back in so that it kind of sets it up for it, because it knows that it's a drive click motor. It knows that, hey, the second it comes out, then I'm good. One other thing, if you notice here, you have motor names and you also have like signal module names before. One thing that I guess I didn't talk about, let me put this, kind of going back and forth. When I put this in and attach this encoder, this is actually, if you notice, it still has a signal module and it still has a drive click cable. And so in this case, this would be using an SMC 30, maybe, because it's an HTL without the sine cosine. Any of you, I see that I have at least one application engineer that was in the chat before. If you are fluent in S120 technology, tell me which, let me know which for a regular HTL encoder, oh, it says it right there. It is a SMC30. So I do remember a little bit of stuff. Sorry, Measure. But yeah, so that tells you what, if I were to put a different encoder in here. So like, for example, if I were to put a sine cosine encoder, like is on a 1PH8 with those different tracks. So you have like this ABCD with a reset. That's kind of the default on that. If you look at, where does it show it? Measuring system selection. Yeah, encoder evaluation selection. So here it gives you two options. So you either have an SMC20 or an SME120, which the terminology here, and I'm throwing way too much at you, I'm getting off track, but the SMC is signal module cabinet and then signal module external. So this guy you could actually set up to where the cable is out in the field and you're connecting it into, this one would be into like a, it would be an M17 connector, and it's got all the pins and everything. And then out in the field, you could plug that cable in, and then it would be drive click cable, which at that point, it would just be a standard kind of Ethernet cable. And so take your drive click out in the field, and then you plug your module into this external SME. But anyway, so all that to say, depending on what type of encoder, external encoder you have, you will have different evaluations. You'll have different signal modules. Okay. And that's why this one here, it has what's called a signal module internal, SMI. And so you'll see some of that terminology when you're looking through some of the S120 stuff, like in the actual drive program. But again, all right, y'all got any questions? Feel free to hit them up. If you are joining in the stream for the first time, welcome. Say hi in chat, where you're from, welcome. If you are getting something from this, be sure to hit that like button to get it out there. We've probably got at least another hour and a half. This is going to be a long stream. We're making up for lost time. And so there's plenty of time for other people to see this, to share it, to get them out there, get them part of the community. And if you haven't subscribed, there's a ton of information that you can get, and subscribing helps get that information out there to everybody else. Romania, awesome. I love seeing, we have a lot of people that are in kind of the Western hemisphere, and I love seeing kind of like Europeans, and kind of, it's a little like the Eastern, kind of like Southeast Asia and stuff like that. What, it's like 3 o'clock in the morning right now. Well, no, maybe it's only like 1:30. Mexico, awesome. Yes. Yeah. I just love seeing Europeans that are hopefully off work, right? Like you're sitting back, you're chilling out in Romania. You've gotten off work from a long day. You're wanting to kind of learn a little more, as you relax and unwind. So I love seeing everybody from all over the world coming onto the stream. So we have got our drive system set up. And one of the things, at least the hardware, one of the things that we're going to have to do though, is set up some way to, and I just realized I may need to actually run these in vector control because my Telegram may not be available. And I wish that I planned that ahead of time, but it just popped into my head. So if you're not familiar with what telegrams are, there are a couple of different videos that go into real details about, that I've put out, that are about telegrams in S120s, G120s, PLC to drive communication. But this is all of the information that goes between a PLC and a drive. And depending on what type of control you have, in this case, we have these set up for servo. Depending on what type of control you have, different telegram options are available. So let's go through and look at this. And I think you have to click on the control unit. Yep. So we're looking at mandrel, and we are wanting 352, and it is not available. And I'll tell you why we want 352. Because I have I cheated a little bit. I have a library that I've designed a control block that has the ability to do the type of torque limiting that we're going to be doing here, and it uses a 352 telegram. And so I have this data type here, this drive 352 in and drive 352 out, and I'll talk about those, but I want to use that telegram 352. And so one thing though that I will talk about here is, remember we said earlier that we're not going to be using technology objects on this. That opens us up to use basically whatever telegram we want to use. And I have a live stream where we really talked a lot about how to use free telegrams to do this load sharing. And I won't go into as much in it, but go back and look at those live streams, put them on at your lunch break and just kind of listen to them, let them osmosis into your brain. But free telegrams are extremely powerful, but they have some drawbacks. And so what I have done is made a 352 that has a little bit of extra information in it to do what we want. Problem is, 352 telegram is not available on servo axes. So let's go through and go back and change all of these to vector, and it'll probably complain about stuff and whine. And oh, it even took our motor, because guess what? Oh yeah, Lucid. Yeah, you'll definitely be definitely want to come back for this. We're talking about all sorts of cool stuff that's in your neighborhood, and I'm glad the accumulator looks good. I think actually some parts that are going to go on your accumulator just finished printing. If you notice, all the noise in the background stopped for those that have been here on the stream. I've got some cool stuff that I might show you later. So because we changed the control mode on this, it takes the motor out, because worst thing would be that it would let you keep a servo motor or like an actual permanent magnet motor in place when you are using vector control, because bad things would happen very quickly. Actually, probably nothing would happen. The odds of something crazy happening are very small, but most likely it's just going to lock up. The motor's going to heat up. You might burn some cables or something, but hopefully your overloads would trip by that point. But not good. So let's go back into our hardware catalog and throw another drive click motor in there. We can still do drive click motor, like a 1ph, like we talked about these before, 1ph8 motors. They can be run in vector control because they're asynchronous motors. They're not permanent magnet motors. So we just have to go back and put those in. But that looks like what we got there. Now we should be able to go back and select our 352. Yes. I'm so glad that worked, because that was not planned. Nah, I knew it was going to work. I trusted the process. So let's go through and set all of, so the mandrel, telegram 352, let's set them all up for 352. And again, if you're not familiar with what these telegrams are, kind of what these options are, there's a couple of different videos. So just look around on my channel about PLC to drive communication telegrams, free telegrams. I think I have 2 live streams that we went through them on, like in real depth, doing some cool stuff. And I think have another edited video that talks about all these as well. But so we've got our 352. I'll show you why we want to do this. So from this point, because we have this drive click motor set up, you're good on being able to move forward on programming your PLC. So the way that we're going to set this up, the biggest thing that we want to do is to be able to set the mandrel up to be able to go into what is called torque limited speed control. So there's going to be a little bit of tweaking that we're going to have to do, and we talked about this a lot in the load sharing drive live stream, because it's the same concept. This some will call it saturated speed torque limited. The problem with I'm going to swap over to and talk a little bit about this, because this is a really, really important thing to think about in this industrial winder. Because a lot of times you'll be like, okay, I need tension control. Tension control is torque control, right? So that's what tension control is torque control. Well, the problem is that tension control is assuming that, or I guess torque control is assuming that you can make your torque set point. So if you're not familiar, you have servo control, vector control, and then you have torque control. And those are actual control schemes. Both vector and servo are speed controllers or N controllers. So vector and servo control, they control speed. So okay. Torque control, as opposed to torque control. Anybody have a guess at what torque control controls? Yep, it's TRO. It doesn't control my train of thought. It controls torque. Yeah, it wasn't a trick question. That was one of those SAT questions that try to trick you. It controls torque. Problem is, if you're familiar with kind of how, I'm going to go through the physics of motion at some point, and we're going to have a live stream that is just physics. Because if you don't know this about me, I graduated from the University of Alabama, Roll Tide, with a degree in electrical engineering with a minor in physics. And most people don't realize in electrical engineering, there is a ton of physics involved with electrical engineering and control. And so I'm going to do a live stream at some point that is just the physics of control, and no TIA, no portal, no nothing, just the physics. Because a lot of this stuff, I take for granted the fact that you might not be exposed to the fact that the speed controller controls a torque controller, and a position controller controls a speed controller. And so you have these controllers that are cascaded controllers. So a position feeds in a speed set point. A speed controller feeds in a torque set point. And I have like N, and like torque is also N, but just sorry. But so it feeds in, we'll call it like torque. I think it's like a weird torque symbol. Motor model chart opens up. Yeah, so measure put in there in the chat for those that are watching this on demand. Put that you can change the 1FK7 to vector by changing the motor module type in the properties, and it opens up 352. Here's the problem with that. That motor will not run in vector control. And I don't know why that's an option. You should contact your local Siemens support representative on that one, Measure. And I might text him personally and ask him why the heck that's an option, because a permanent magnet motor has to have a pole position. And so again, getting off, I have never once gotten off topic. I don't know if anybody has noticed that, but I don't have ADD. So like in a motor, see, all right, so he just Measure put in, he was like, never mind. Never mind. It won't let you add the 1FK7 after you change it. Yeah, because the thing about so you have like a north and a south, and then you'll have like a north. This is again the physics of motion. This is part of physics. That's north, south. So you can kind of think of a motor kind of like this, where the rotor has especially in actually, no, this is drawn wrong. This is a bad way to draw a permanent magnet motor. So in order to, so you have a rotor field. So think of this as like a north and a south pole on a motor. And the way a motor turns is you want to have like a south pole here and then like a north pole here on the outside of this frame, right? That's kind of what you're trying to do. And then you're trying to move this around in a circle, and then this will track behind it, right? So if your field kind of leads your like this, and these two fields are not in sync, and there's a gap, that is an asynchronous motor. And there's you can have an asynchronous servo motor, you can have asynchronous induction motor, like yeah. But any motor to where these things are designed to be in sync, they only work when they're in sync. If they slip, then they get out of sync and they don't turn, they stall. And so this is a synchronous. That's why in synchronous. See, I wrote synchronous. So they're in sync, whereas asynchronous, there's a little bit of lag. Well, the only way that a synchronous motor, and there are synchronous induction motors, so don't think that only permanent magnet motors are synchronous. There are absolutely other types of motors that operate synchronous that are not permanent magnet motors. But all 1F, K, T series, all those 1F, so there's even 1FLs, and then there's the LMs? So there's a full series of motors that are with the Siemens product line that are synchronous motors. And if a motor is synchronous, you have to know where this pole, and when I'm saying pole, you have to know where the pole is. And there is some functions that you can actually get away with in not having an encoder, but a vector model does not work with a synchronous motor at all. It just does not, because a vector is doing a calculation. So you have the motor field, so the rotor field, and then you have the static field, so the actual phase field. And if you're not familiar with what the term vector means, it is a term in calculus, or really from spatial coordinates. It's a line between 2 points. And so you are creating a vector. It's calculating the vector here. Okay? So that's what the vector in vector control means, is this slip. It's calculating this vector, and so it can know, because it's controlling this, it can know where this is based on this vector. With a permanent magnet motor, this doesn't exist. There's no vector. It's always zero. The vector is always zero. Otherwise, it's not moving. So a vector calculation doesn't work. And so you have to have servo control in order to do a permanent magnet motor, or a synchronous motor for that matter. So that is way off topic. Where were we? Torque control. But good job, Measure. Like that's a great point and a great discussion about motors, and I will definitely go more into that in our physics of motion. It'll probably be 3 or 4 weeks down the road to where I want to do just a straight physics thing. So I'm going to clear this and start over. So we've been talking about torque control. Problem with torque control is you just set a torque. That is an O. T-O-R-Q-U-E. Torque control equals torque set point. Okay? And that's really cool and fine and dandy to say, hey, I want this motor, which is turning this way, I want it to have a torque of 10 Newton meters. One day I will figure out how to write a 0 or an O without making it look like either E or theta. So I don't know why. So if we set torque control to this and say this is a wire set to a block that is grounded to an infinite plane. Yes, a synchronous motor can be does that seem like a stepper motor? Kind of. A stepper motor is a type of synchronous motor, because a stepper motor has a permanent magnetic field, and so that's where you're getting steppers, because it's stepping between the poles. And so that, in order to generate torque, it is trying to be aligned into that field. So that's where a stepper motor works. So if a stepper motor gets out of sync, then it's going to stall, because it can't generate torque if it's out of sync. That out of sync is called slip, and in an asynchronous motor you have to have slip, otherwise you can't have torque. In a synchronous motor, if you have slip, you don't have torque. So I mean, that's not 100% true, but that's the easy way to think about it. But so we're talking about torque control here. If this is connected to like the ground and grounded out, and this is perfectly connected and perfect, then this will easily be able to hit 10 Newton meters. It puts out enough current into that motor. It puts 10 Newton meters, and then that's all it puts out. And so you can do like a physics calculation of whatever, how much force is on this sheet and all that stuff. Like you can go through and do all of that. So there'll be some force here, which is kind of equal to tension, right? Well, in torque control, what happens if you cut that wire? Well, the torque goes to 0. So the torque seen by this motor goes to 0. Right? Well, you have a torque set point of 10. So what does it try to do? It puts out more current, and it's not getting any resistance. So it starts to speed up. Well, guess what? It's still not getting any resistance, because it's just sitting there free spooling. So it keeps speeding up and speeding up and speeding up. It's called a runaway. And obviously, there's all of these American like 80s songs that are going through my head about being a runaway. But so obviously you don't want your drive to run away. If you want to see what happens when something runs away, I'm sure that there are some terrifying videos in the dark parts of the internet, or some of them where there's not death involved. But this is a really quick way to destroy a lot of equipment, possibly in someone's life, probably most definitely in your career at wherever that is. So you do not want a runaway condition in a motor. Most of the time, again, these motors are pretty big. So torque control, like true torque control, is dangerous. Sometimes it's necessary and you just have to deal with it. But true torque control is dangerous. So anytime that you can, you want to avoid torque control. Why? Because it's only looking at torque. It knows nothing about how fast the thing is moving. And so in this example where this breaks, all it knows is, hey, I'm not reaching my torque set point. Put more power to it. I'm still not reaching my set point. Put more power to it. And the next thing you know, yeah, bad things. So what we want to do is we always want to kind of wrap this with speed control. Right? We always want to wrap this around it and say, hey, no matter what, don't go more than 100 RPM. Right? We want to say, no matter what, don't go more than 100 RPM. Well, the way that we do this is what we've talked about before, with what's called a saturated speed controller torque limited setup. It's not torque control, it's torque limited. I'll show you how to set it up. And we'll clear this out. And what we have is we have a motor here, our mandrel motor, right? And we're trying to generate this torque. Back to this block, okay? And again, this block in the future isn't going to be a block, but this is the simplest way to think about it. So what we would want to do is say, hey, motor, I want you to run at 100 RPM. Obviously, if this is like blocked into the thing or into the ground and it can't move, you say, I want a end set point to be 100 RPM. Okay. Now, if you just do that on a regular drive, it's going to output 100% torque and it's probably going to break this and then start running 100 RPM. So it'll try to do that. So what you need to do is we want our set point here to be 10 Newton meters, right? Well, we want to have a torque limit equal to 10 Newton meters. Okay? And so that's what we would do. Now, obviously, it's never going to reach 100 RPM, right? And so the output from the speed controller, and kind of remember we talked about our end controller feeds a torque set point into our torque controller, and then that goes to our actual IGBTs. So like that's actually our inverter bridge, right? So that's actually controlling current and all of that stuff, right? We all know that. All right, so that actually goes out to the motor. So this speed is never going to reach it, because so we're getting our feedback into here, and it never reaches it. So this is eventually going to go to 100% torque. Okay, so it's trying to reach that 100%, or it's trying to reach that 100 RPM, and so it's gonna put out, and say, hey, you're not going 100 RPM, and so it's gonna say, eventually it'll build up and say, do all you can. That's called saturated. Once you hit 100% in a controller, you don't get any control. It's doing 100%, and whatever it's doing, it's doing. That's called saturation. Okay, so that's what that is. So here, though, you'll see a little block called a limiting block. So when this comes in, it looks like this. And we're going to take this and say, all right, say this is a 100 Newton meter motor. We're going to limit this to 10%. Okay. And so even though this is 100% torque going into this block, what's going to come out is going to be 10%, which equates in our perfect world example to 10 Newton meters. And that's how we will achieve this. So then, if for some reason, whatever happens here, if this breaks, then your torque here for just a split second will still be 10%, and it'll start to accelerate, and it's still only going to get 10% torque. But once it starts getting close to this feedback of 100 RPM, so once it actually starts to get back into close to 100 RPM, this will decrease down and will go to like 0.1%. Okay. And then you'll only, instead of be outputting 10%, you'll be outputting 0.1%. Just enough to keep it moving at 100 RPM. That's the speed controller catches it. And so that's the saturated speed controller, torque limited control scheme. And so that's what we're doing. If you have any questions on this, again, I talk about this in depth and some of the things that again we'll be going through in the load sharing, because this is the same concept of load sharing. If you have multiple motors trying to match their speeds, you're going to do the same thing. Same thing with a winder. It's just a little bit different thought process of keeping that tension control. So if you got questions, hit them up in chat. If you're watching on demand, hit it into the comments. All right, so we've got our physics. So what we're trying to set up now. So the first thing, we're gonna go back to that off, click that, and I'm gonna click this. Or am I going to click? Yeah, I'll click this right now. Remind me, do me a favor. Remember, if my head blocks something important, if I'm talking about something and you can't see it, yell at me in chat and hopefully I can see you. Screen's over here, chat's over here, but I can still see it moving over there. So let's go in, and first thing we want to do, since we've set up these 352 telegrams, I want to show you kind of how to set up a kind of a custom way so that you can understand how to control these motors and what we're going to be doing. So we're going to set up the PLC side first. And what we're going to do is we're going to go into the PLC tags, and we'll just go into the default tag table. And I'm going to add in just a couple of things. Mandrel in and mandrel out. Knife in, knife out. And obviously I'm going to change all these data types here in a second. And then metering roll in. So what we're going to use is what's called a PLC data type. And I'm going to cheat and use one that I've already made beforehand. We talk about this a good bit in the other free Telegram stuff, and I talk about data types. If you want to take your your Siemens PLC programming to the next level, and you want to like separate yourself out from the crowd, learn about PLC data types. In regular programming world, you can call them structures, but yes, PLC data types, structures will set you apart and set you up for success, and for vacations, because these save a ton of time. So what I'm doing, I'm just going to drag these data types that I've already made, my 352 tel in, and then my tel out. Oh, it went away. Yeah, there we go. And when I set these in, what these are, I'll show you what these are. So this is actually the 352 telegram. And this type, or this data type, has all of these bits and bytes and all of that I need in order to set stuff up. Now, this is not necessarily the 100% 352 telegram, because 352 telegram doesn't have all this information, but it has, especially in the send direction, it has some what are called user defined, and you can just freely connect them and still use the 352 telegram. We'll do that here in a second. But what this data type does is it organizes all of those bits and bytes and words and all of that into stuff to where you can access it just like a tag. Otherwise, you're going to have to keep up with that on your own and do memory locations, and it's a pain. This is the best way to do it. And obviously, I set this up years ago. I made this data type, and now I just use it. I always use 352 on my vector drives and just use it. And I'll show you on the out, we have these guys here, the upper torque limit, lower torque limit. And we still have to connect those on the drive side, but in this setup here in this UDT, that's what we're doing. By the way, yeah, UDT structure, all the same thing, PLC data type. So now what we're going to do is we're going to go back to our tag table, and we're going to rename these of, this is going to be a tag in, this is going to be a tag out, this is going to be a tag in, and obviously it doesn't like them, and I'll show you all the stuff that we're doing. So tag in, tag out. Yeah. And now that I've done that, I'm going to go ahead and move my head over to the other side, because this is more important. This detail view over here comes into play later. And I always cover up the detail view with my face. So, inputs are going to be inputs, right? But what input address should we start? Where do we find that? Because this is the telegram, remember? So let's go back and click here. And which one are we doing? I have a memory of a goldfish. So we're doing mandrel. So let's go in here, click on mandrel telegram. That's what this is. And then we're going to look here, and starts at I266. And then the receive, which in this view here, this is from the drive's perspective. So the drive is receiving this. That means the PLC is sending it out. That's why it's IQ there. So I266, Q266. So we're going to go back and set those. I will say, if you are setting these up kind of like intentionally, and you've done this multiple times and all that stuff, normally these addresses are going to be the same. So it's going to be I266, Q266, I whatever, Q whatever, same thing. But it's not always the case, because sometimes if you don't have enough room in your registers there, it'll move it to the next. It's inserting it into the next available slot, not necessarily just where it is. Because Unlike other things, you can absolutely 100% put two things that overlap in memory, and then you'll start controlling this area data here will get controlled by two different places, and it will drive you insane. Okay? That is the worst thing to do, so avoid it at all costs. But yeah, just go in here and check and make sure that they're the same. These are 266. So we're going to go back to our default tag table. And it's going to be IW 266.0, I believe. Nope. It's just going to be I. So Q 266.0. And I'll tell you one thing. Because the reason I'm having to do the .0, even though it's a word, is because the first use of this tag is actually a Boolean. So the first place that it's being used here is a Boolean. That's why I have to use the .0, because you'll see me sometimes like kind of mess around with those sorts of things, and I'll put in like an IW like I did there, and IW is the first word, and even though this is all in words, the first thing in the tag is a .0, so that's where it starts. So that's why it's a .0 there. So now let's go check all these other ones. And again, this is the knife and the meter. So we're gonna go to knife. Check that. 290, 290. 290, 0. Metering roll. 8. Always check them. 78. 78. 0. U278.0. And that's your basics. So I've had a couple of discussions about like these big telegrams and everything like this, and it getting what's called discontinuous data. If you're working with Profinet, you don't really have to worry too much or as much about inconsistent data. But if you are using a DP, so Profi bus, you might want to check out it's a DP read data. And I have a block, or I have a video, an edited video about how to use that block and why you would want to use that consistent block call thing. With Profinet, it's not so much. This is how the technology objects do it. They use these what are called interface or actor tags. And so this works. This is the easiest. It works well in Portal. It works well on modern processors. Just if you're using like a 300 or 400, you might run into some issues in some very rare cases. But watch that video about DP. So it's DP read data and DP write data, those blocks. And so let's go here. So now that we have that data, what we would want to do is we want to set up 3 different, we'll just do function calls, because we want to do mandrel. I would love to have it capitalized M. Mandrel. Roll. And I'm just making a couple of where we could put all of our control. Mandrel. Knife. Control. Finally. Eventually we're going to be wanting to control the bits and bytes and stuff in that. So go ahead and make those. Save. Coffee break. Cold coffee. Yes. Guess it's kind of good. Tasty. But so up to this point, we are just getting kind of started in the actual controlling this. So let's think about what we're wanting to do. Let's go from the mandrel. And this is going to kind of show a way that I kind of process through things when I'm writing code. I will go through, and first of all, this is a weird little thing. I don't know why it does this, but I always make a second network and start on second network. In all of my code, network 1 is blank, just simply because if I put something here, it always puts the logic below it. If I say insert network, if y'all have a way, if you know of a way to insert above network 1, let me know in chat. Like, for real, because it'll eliminate, because I always leave network 1 blank because of this. So what I want to do is, the first thing that I want to do is go through and kind of like get a thought process of the steps that I want to do. So the first thing I want to do is enable drives, and for this it's going to be very, very basic. So I can also do just, I think it's what, Control Enter, or is it Alt Enter? Control R. That's the one. So then I want to create for the mandrel, create speed. Okay, Control R. And then I want to create torque limit. And then run motor. Okay, so with a mandrel, you're always going to have two things: speed control and a torque limit. Now, if you're just winding it by itself and you're not concerned, you are actually wanting to run in speed control, then you'll have your torque limit set to 100%. And so we'll talk about that in a minute. But this is basically what you're going to be doing for that drive. You're going to have your enables, so safety circuit, all that stuff, and stuff that's going to get tied into that telegram. And I'll show you how to do that in a second. We're not going to go through the knife because that's a little bit more complicated of topics. But basically for it, you would want the same things, enables, and then you are going to have a couple of different modes to where if you want to jog and home and everything. But for it, you are going to want to set up something to where you want that knife to be able to hit at a certain point, right? So that's the goal of the knife, and that's a little bit outside of what we're doing. We're trying to really do this wind, unwind. We're going to assume that you're going to wind it and you have a clamp and it comes down and cuts it, okay? But we might do this knife at a later time. So that's why I'm just going ahead and include it here. So for the metering roll, we're gonna do the same thing. We're gonna have our enable. We are going to have our speed set point. Then we're gonna have our length And I mean, this is going to be a very rudimentary way, and we'll build on top of this. The big thing about this that we're doing is that tension control part. So just remember, so start. And so we're going to do a very rudimentary, like this would not, you wouldn't want to do this, and like there's other ways that you'd want to do kind of stuff, because you're going to want to have some sort of position controller, but we're not really going to be worried about the position controller right now. We're not really going to be doing the length portion of it. So we're going to say future on this as well. Okay. So that's the basic setup that we're going. And obviously it's a little bit more complicated for like a full system. If you want to see some actual code that is running that winder that's in the thumbnail for this stream, there's a couple of other videos where I talk about like using actual code and like going through that actual code. And that is that code. And it's a lot more complicated than this, but we're just wanting to set up that tension control. So that's the basic flow of what we're wanting to set up. And so the thing about these, we're going to look at the mandrel out. So this control word, what we're going to have to do is we're going to have to set, I'm going to highlight everything that has to be set in order to have the opportunity for it to actually run. So we're going to do control by PLC. So this on here, that 12, that is, that's, I guess, that's what actually starts. So that has to be off. Everything else has to be on. Then you turn that on. So that has to see a positive cycle with everything else on. So we're going to go through and set no coast stop, no quick stop, enable operation, enable ramp function generator, unfreeze, ramp generator, enable set point. I know that sounds like a lot of stuff, and it is. So let's see if, so that's all the stuff that we want to do. Now, we can go back and forth and see all of this stuff, but I'm going to show you how to use this details view in this bottom left-hand corner here in order to really think this up. Because what we're wanting to do is I want to go and I want to set all of those, and I don't have to be going back and forth all the time. So I'm going to go to those PLC tags here, right? I'm going to click on the default tag table, and it brings up down here in the detail view whatever that is. If it can pull up stuff there, and I want to go to my mandrel out, and I actually select that, pull it up just like I did before. I kind of move this over, and now I can kind of go through and I can start doing this. I can start hitting this down here, and then 7. Okay. So shift. So shift 7. Nope. So we're gonna do, actually hit shift F7. It's not doing it. Why? Oh, because it's the wrong thing. So I was gonna show you that this is more quicker to do it this way, but let's do it like this. So I want to drop down, I want to put a branch here because I want to do it like this. I want to drop down there. Now I'm going to take out of this little thing. First thing, I'm always going to have my control by PLC on. And why is it not letting me drag that? Okay. So we have to start mandrel out dot control word dot control by PLC. I don't know why it won't let you drag the bit there. That's weird. But it's keeping it to where, yeah. If you know a way that you can drag that out for you Portal veterans in here, because it's inside of a structure, it's not letting me drag out of the detail view. But you can always do like I'm doing here, click just mandrel out, and then control word, and then look at it. I want no coast stop, like that. Then I'm just adding in another one, and then this mandrel out. So it's a little tedious to go through and do all this. No quick stop, like that. But it's something you got to do. Now, here in a minute, because we've used this same structure, maybe we'll do something a little find and replace here. So, mandrel out, control word, dot, enable operation. Drop another one. That. Everybody that's programmed knows that there's always a little bit of delay a little bit of tediousness on everything. So we're just going through and getting all of these enable ramp function generator. And if I was using the shortcuts, it'd probably be a little bit better. And then it's unfreeze. And the reason I put that little contact in front, so enable set point. The reason I put that little contact out front is because otherwise it won't show up like this and they won't be tied together. And there's a reason for that, because you want like an e-stop, you want like a safety. You don't want to enable this stuff if the safety's not made up. And so that's what we're just putting that in there as like an e-stop input right now. So enable set point. Set point. All right, so we got that. We're gonna save this. Let's do this. Let's make another block. We're just gonna make a data block called safety data. Okay. Normally this might be coming from like your actual safety program over here. This main safety stuff over here, like you're actually bringing in your e-stops into your circuit, and you can use safety inputs. So safety blocks you can use in non-safe, but you can't do vice versa. But what we're going to do is we're going to have a safety data, and we're just going to add our system e-stop like this, and we'll modify that elsewhere. But what we will do on our mandrel is we will now use safety data and then system e-stop there. So save that. Now what I want to do is I want to control C and then go over to my metering role and then just do a control V. That. So I did the whole thing. Enable drive. So now I have this same structure that we just took the time to do that, but I have this mandrel out here. So so find mandrel out, replace with what is the name of that? I'm just wanting, it's mandrel out or metering rollout. Right. Found, find, match, find. Okay. Why is that not letting me do it this way? So I want to replace, replace. I'm not doing replace all because it's a whole document. And just go through and just replacing all these. You notice it is updating it to place, right? So I told you it'd be quicker. Do it right once and then copy it, and then you're just doing a find replace. And I just replaced that word. And again, going through and naming things properly, using UDTs, using all these things make for efficient programming. And we would be able to go through and do this exact same thing here on our knife, but we're not worried about the knife right now. So we've got our enables all set. Yeah, Lucid. I think so on that dragging, I think in the details view, for some reason it won't let you drag a like this. So like if we did like a move, like it won't let me pull that. It's just weird. I don't understand why. Maybe we can all band together and all email Siemens, be like, hey, let us drag out of the yeah, it'll do it from a data block for sure. Like it definitely works like inside like the static of a either a data block or a function block. Like if you're in the interface, It's just something to do with the detail window. Let's all band together and email your local representative and say, hey, we want to be able to drag out of data types out of our detail view. We want to be able to do that. That's what we want. We want it now. Probably more important things to protest, but hey, if you don't have anything to protest, let's do that. Let's do that. Let's all band together. All right, so next thing I want to do for this mandrel is we want to go through and we want to create a speed set point. And so what we are eventually wanting to do, right, is we're wanting to move something into this mandrel out speed set point. We'll do that. And so this is going to be 0. So speed set point is plus minus, was it 16,384 equals plus minus 100%. So this number that we're putting in here needs to be scaled to 16,384. So 0 to 100%. And so whatever we go through and do, so what we can do is, in this case, we're using function calls. You may, if you're doing this a lot, use a function block so you have static memory. So let's just go through and add in a new block because we want a little bit of data for our mandrel data, right? And we'll probably want some of that for all of them. So let's just make a function block for knife data. And finally, again, we're taking our time, just going through. But this is kind of the full process from scratch. So now, I'm so dumb. I made those function blocks somehow. Why did y'all tell me? Put everyone can spam. You're so dumb in chat because I clicked the wrong thing. So let's try that again and actually make a data block. Mandrel data. I was wondering why I wouldn't pull it down there. Knife data global DB. And then all right, global DB. All right, so now we have these, and so what we're wanting is we want a speed set point, right, from our user. So we want our mandrel data. We want right. Let's do real. We might want to do that, right? And then we're also going to want a torque set point. Right. And then from our metering roll, we're going to want the same thing. Well, we'll just want a, for right now, we just want a speed set point because we're wanting it to pull at a certain speed. Okay. So we're going to go to the mandrel. And eventually what we want to do is get that kind of block into a place to where it's this output for this drive set point output, right? So we're going to bring in and do some math, right? So we want to divide our number by 16,384, right? So let's do a division. And we'll do an auto and see what this, and I'm going to try to kind of, again, we're building stuff up from scratch. So we want to do manual data, right? We want our speed set point. We want to divide it by 16,384.0. Just by the way, if you don't put the 0.0, it don't like it. No, actually, it puts it in for you. Because 0.0 is a real. If you don't put it there, it's an integer. And it says, hey, this is real division. So you're there. So where do we put this? Well, what I'm going to do, what I normally do is have temp real, temp int, or temp dent for this case. So we're going to do temp real, and it'd be a real. And so a temporary is only available for while you're in that block or in that cycle, or not the cycle, but in that run through of whatever block you're in. So you can use this all you want through there. Steps along, if you update it, then it gets updated. Next rung, you can do whatever. Then once it leaves the block, it gets blown up, deleted, it's gone, comes back in fresh. So these are just for these calculations. Dent, and we'll need these, and you'll see why here in a second. So what we're doing, and we'll just put temp real. Apparently, it could do an automatic conversion to dent. But what we need to do now is we want to take, because that's the division, and that is from 0. That's just the number, so that'll come out as like, did I do that right? Nope, I did that wrong. This is backwards. So this would be if I was bringing in the analog input. We did this on the last stream. That's why I got confused. So we're wanting to output something by 16,384. So what we're actually wanting to do, this value here, we're going to say is a percent. Okay. So what we're actually wanting to do is divide this number by 100, right? And then that'll get us that point whatever. But if it's 0 to 100, we divide it by 100, it gets point, and then we want to multiply that by this number. So we want to divide it by 100. Goes into temp. We want to multiply temp real by 16,384.0, right? We can do temp real again. Now that is our set point, percent set point based on the percent set point based into the 16,384, which gets sent over to the drive. Well, now that's a real. This drive has to be a word, okay? Or so an integer word, same thing. So we need to get this real into, so we're going to use a converter operation. And for this one, we just want to round, okay? So we want to round our temp real, and we're going to make it temp dent. Then we're going to move that temp dent there. Okay, jam it in there. So here, what we have is so that should compile. It did not compile. It says, oh, I haven't compiled all this other stuff. Let's do it this way. All that. Yeah, so it's just compiling everything that was there before. Stuff wasn't compiled first, so that was what that error was. So, all right, it did it. And by the way, so I just clicked there and selected that program blocks. and that's going to compile all the blocks that are associated with it. I could also like click on the PLC, right click, say compile, software rebuild all. I could click here, click up here at the compile. Tons of different ways to do stuff. So what I got now though is something in my way. Control 5, get that out of my way. And so I've got my speed set point in percent. So this would be like how the user would interface. I want to run it at 5% speed, something like that, 10% speed. And that's how fast you're wanting this manual to run as like a maximum, okay? Well, we're gonna set that and dividing it by 100 because that's in 0 to 100, right? And so then we're gonna multiply that into the 16384, which a drive based, we want to be able to go up to 200%. So we have a bit, because it's 16 bits. And so we have the first bit is the sign. The second bit is to make it to where it can go over 100%, because you can actually command these drives to go up to 200% speed, 200% torque, but then the drive will just limit itself appropriately depending on how it's parameterized. Okay? And so you got your speed set point out. Now that seems like a pretty good block, you know, because we're going to have to use that on the torque set point as well. And then we'll have to use it on the speed set point from all the other stuff. So let's do this. Let's real quick. And I know, again, this stream's a little bit longer, but it's all right. It's going to be a couple weeks before we get back. So you can come and go as you please. But let's take and make this real quick into a function block. I'm just going to copy all this code, okay? Because I like that, you know? And actually, I don't even need, it doesn't even need to be a function block. It can be a function call, because everything in here is either an input, a fixed value, or a temporary value. Yeah, so we got an output there. So we got an input, output. So let's make a function call that does this for us. And this will kind of show you, if you're not familiar, kind of just driving home how to use function blocks, function calls, FCs, all that stuff. So let's make a function call called percent to drive word, right? Pretty fun name. And we're going to make a comment that says this converts a real 0 to 100% to value for drive input. Right. Okay. We'll click that. We're going to open this up. We're going to Control V that. Now, obviously, this stuff isn't there. So let's make our temp real. Okay. That needs to be a real. Real. And then let's make our temp int. Here. Int. And again, I'm doing stuff multiple times, but this is probably how you would go through and do something. If you're just kind of go through. So obviously there's no hashtag on these. So we don't want to use a fixed value. We want to use this block over and over and over again. So what we want to do is make this an input, because we want to input this in. So we want to call this percent in, and it is a type real. Okay. And then now we want to replace that with this. Okay. If that doesn't make sense, maybe it'll make sense in a minute. And now we want to take this and replace it with drive word out. And that is a word. Okay. Right. That's the type. And then we want to replace this here. All right. So now we have a fully portable block. We'll be able to use this no matter what, and we'll parameterize those inputs and outputs here in a second. We've got that. So let's save this. Now let's go back to our manual control and let's just take this and delete all of it because we don't need it anymore. Because now we package that all up here. And you're like, Jason, why in the world are you doing this stuff? This is a waste of time, right? Manual data. And then we say our speed set point. Manual data. But no, not that. It's manual out. Yeah, our actual output. And then it's going to be our speed set point, right? Connected, right? Now, here's why I did it. Do this. Manual data. Work set point. Manual out. Upper torque limit. Because that's what we're going to be capping. And we're going to be good there. And I'm done. That's it. That's why I did that. And now, take that even to the next level. If you didn't kind of guess what was going on, we're just going to drag this in again. And now, instead of manual, we're going to say, this is the metering roll, right? Metering roll data. Because we've set all these things up beforehand. We're going to do it right, right? Metering roll out. Then we're going to go speed set point. And now, it's all connected. There we go. And those two drives are being controlled now. Honestly, we got to do a couple little things, like the start motor stop. So, let's do it like this. We're not gonna do that. We'll do this. We'll do go back, start our manual. So got our enables, got our create set point, got our run motor. Let's do this. Double tap. Then we're gonna bring in our safety data. This is me stop. And then we're going to make in our manual data, we'll just make, this is a really bad way, by the way, of doing this, because you want to put all of your booleans up at the top. You don't want to be like adding in stuff. It just makes things messy, but we're just going to do this. So start, yeah. And it just messes up all these offsets. And if you're using what's called optimized data access, which we are here, it doesn't really matter because it's all kind of tag based. But if you are connecting up to like Ignition, you would want to structure these a little bit differently because Ignition has to use offsets, or any SCADA platform would have to use offsets in order to reference these UDTs. And it wouldn't be able to work really well with this type of structure. But for this, it's about the concepts, and go to the metering roll data and do the same thing. Start. And but we got this. And so now we've got a metering roll. And now we want manual data. Start manual. And here for our output, we want to go through and select that manual out, control word, and then just the on. That's it. So again, talking about this enables, these enables all have to be on before you get this on. Otherwise it won't enable. So these have to be two different things. So you can't trigger them at the same time and go across in the same cycle. It'll never come on. And it'll be really confusing why it won't come on, because it won't tell you why it won't come on. It'll just be not coming on. So got this stuff. This is fairly basic. So let's go back to our meeting roll, and then let's do our start. We're gonna do the same thing. Hit. Then system data, or safety data, system stop. Metering roll data. Start metering roll. Metering roll out. Control word. On. Boo. So we've got that. Now, honestly, this would start to work. If we had a drive system, we'd turn on our e-stop, and we would set our speed set point to whatever this is the metering roll, and while it's running, this is what's actually going to control the speed of the line. And so we don't have to have the stop, because this is just kind of like if you have an infinite like really massive, huge whatever roll, and you're winding off, and you're just kind of unwinding slowly, and you're rewinding things, this would do that. Now obviously, instead of running just a speed set point, you would want to use some sort of position controller, and there's one that's available on the drive that we may talk about later. It's called ePOS. There is also tons and tons of videos on this channel about technology objects, but remember, we're not using technology objects on this one, in this particular application, because we want to enforce the concepts across everything. So last thing we need to do is we've got to set up these drives a little bit. And so hopefully in about 20 minutes, I'll be able to set all this up. And so what we're going to do is we're going to go in, and let's go into this drive CU, and let's go to the actual mandrel, because it's the one that's going to be torque limited. It's going to be the one that's the most kind of the most critical. The other one's just speed control. It's going to be running at 100% torque. You're not going to modify. You're not going to modify the metering roll drive. So you're going to have to perform. You're going to have to make these modifications to any drive that you want to be able to be torque limited. Okay. So what we have here, we can go here to open torque limiting. And here is the upper torque limit. Okay. We click on the upper torque limit, and what we are actually wanting to do is change the scaling. Okay. So someone would be like, "Hey Jason, why don't you change the actual upper torque limit?" Right? Or this guy right here. Well, one of the problems with this sort of setup is that if you put a negative value in the upper torque limit, it creates a situation that kind of annoying to think about, but if you hit that upper torque limit negative, it actually creates the same situation that we had before in torque control, to where it starts a runaway condition. So if your upper torque limit is ever negative, it can create a situation to where it can be a runaway. So here is a little warning that it's saying about this. So it says an incorrect sign can accelerate the drive. So it's kind of hard to understand, and it really doesn't matter to understand. But if you have a negative upper torque limit, the chances are you're going to have a runaway condition of the drive. So it's going to try to accelerate while it's trying to limit, which doesn't make sense, but it's because it's trying to, it's not ever able to cap. So an easy way to do this, and to avoid kind of some problems, is by using this scaling. And whatever that upper torque limit value is, it's scaling that upper torque limit value. And that way you don't accidentally put in just a negative value. Now, obviously, if you put in a negative scaling, it's going to multiply by a negative number. So it's not quite the same, or it's kind of the same, but a little different. So first thing we're going to do, though, is we're going to just take and put this into our PZD, receive word. And we need to figure out which one this is, right? So PZD is, why did I say I have to? I almost messed up. I almost messed up. So in the S120, you actually have two ways to communicate to it. You have the internal IF1, interface 1, and then you have an interface 2, which can be either a Profinet card or communication module. Like there's all sorts of stuff. So I almost picked the wrong one. So this needs to be IF1, so 2050. We need to figure out which one of these it actually is. So the way that we can do this, we'll cancel out of this for right now. Close this. We'll go to our tag, right? And let's look at our tag. So mandrel out. So this is PZD1, PZD2, PZD3. Pretty simple. So upper torque limit needs to be set to 3. Let's go back to our drive. Go back into that dialog by clicking upper torque limit, clicking on the little bico connector, and then going down to 2050, IF1, Profi drive, PZD, and then we want to select 3, PZD3. If you notice, it's index 012, but it's PZD123. So we want PZD3. It's the third word. We want to do that. Now, just talked about doing this upper limit, this upper value here, right? So let's go through and make sure that this value for that torque limit, so mandrel, let's just make sure that no matter what, that is upper torque limit. Let's do something like this. Is there an absolute value function? Yep. Let's move this here. And then let's just use a let's make a temp word. Just for consistency. And let's drag this down here. Drag this down here. So now we're doing absolute value. So we're making sure that we never send a negative value there. Okay. Same thing with the lower torque limit. If you can set the same thing up. So like this is a winder situation. If you are in what's called an unwinder and where you're paying off onto something, then you want the tension is controlled on the payoff side. That's actually an unwinder. And you would want to limit the negative torque. And so in a negative torque situation, you could still use the same block, but your negative torque situation would get it to where you're wanting to limit the amount of braking power. Same thing, that negative torque always has to be negative. So that negative torque limit always has to be negative. So we got that, and we set that, and honestly, that's it. Pretty simple, right? Because you go through, and if we look at the speed set point, right here, or maybe it's right here. Set point channel. Speed set point. We already have Profi Drive PZD2 is already set, because that's the beauty of using kind of a customized 352 telegram. Is this is already set. When we set 352, this goes in and sets this to be that. Whereas with a free telegram, you would have to go in and individually set all of these things. So that's why I tell all of my people, try to start with a standard telegram. 352 is great because it's got a bunch of user stuff to send out to it. All of the user data on it is really just so the entire send out to it is a control word, a set point, and then a bunch of user data, and that's why I use 352. So yeah, so we actually, this would work, and here's how this would be controlled. So we have our mandrel, okay, and on an HMI, we would set our mandrel torque set point. Okay? So the mandrel torque set point is going to be whatever it is. And we're going to finish up the last little bit of this stream talking about the physics of how you would actually set these values. So say, for example, you're going to set the mandrel torque and set the mandrel speed set point. Now, this mandrel speed is always going to have to be higher than the metering roll speed all the time. So one thing we could do is go through, and instead of just having a speed set point like this, we go through and say, hey, we just want to do another multiply here. Okay. And we want to multiply we'll do a real multiply. And we want to bring in the actual speed from the metering roll, right? Because if you always have to be running faster than the metering roll, right? So let's look at this. So let's go to metering roll and look at the input side. So what's coming back from the drive. And it clicked the wrong thing. And this may not work exactly because it's going to be in like an integer. Metering roll in. Because what we really would like to do is just make it to where whatever that speed is gets sent over to, right? Just multiply it a little bit and sent over to. So if we look at the metering roll in, the actual speed is going to be here, right? So what if we just multiplied that by, say, 0.05, right? 0.05, so 5%, right? Well, honestly, think about it, right? We don't even need this. We don't even need all this conversion because we would have to convert into percent just to unconvert it out of percent, right? So if we really wanted to set this up to where the metering roll or the mandrel is always trying to run 5% faster than whatever the metering roll actually is running, we could just do this right here. And we're done. Pretty simple. I mean, and that would actually work. Because instead of worrying, you're not really worried about the set point of the metering roll. You're really worried about how fast it's actually running. And honestly, this is how to do the load sharing. If you've watched the load sharing live stream, this is the exact same stuff that you do in the load sharing. So for this mandrel, the speed set point is always going to be, it wants to run faster than the metering roll. And this would do it. So you're just taking the actual speed from the metering roll. When it's not running, that's going to be 0. 0 times 0.05, 0. And so the mandrel is not going to be wanting to run. Now that might be a problem. Maybe you want to add in 3% instead of just multiplying. So, but all of that to say, you can just modify this this actual speed and say you want like a minimum or something. Then you can always kind of finagle that around. So if you want torque, if you want to create torque like on startup and then like metering roll out, let's see how we would do that. Because right now, if the metering roll is not running, this thing would not generate any torque because it would have a 0 torque limit. So what would we do? So we would want to have some sort of minimum speed or minimum torque, right? So say 5% torque. So let's use what's called a calculate block. Okay. And these are a little annoying. There are better ways to do complex math, but this is all right. So we want our output to be the speed set point, right? We know we're going to want our actual speed to come in, and we know we're going to want to multiply it by 0.05, right? We do this, yeah. All right, so we've already encountered a little bit of a problem, but we're going to have to do a round. If you notice what's going on, I'm changing this real value, and all these red mean that, hey, something's not the right data type. So let's use our little temporary values. Let's move this over here. And then let's use a temp real, round real to int, and that likes that now. And so let's click this little star here to make another input here, because we want to have some sort of like minimum percent speed, right? So actually 5% might be all right, but let's say we always want a minimum of 0.02. I'm gonna have to do this. I noticed, because it's word logic, and inside wait a second. Let's try something. They might be able to do an explicit conversion inside, because we might be able to do this. Might be able to make it work as call it an integer instead of a word. Ha! Look at that. So yeah, so you see this little block right here on your little input. I wish I could zoom in, but on your little input, there's like a little block with a little X thing. That means it's doing a converting. It's converting that value into an integer, like 0.05. And so, who knows if this is actually going to work, because integer division isn't always good, but we'll see. And so what we're wanting is to take N1. That's so dumb. N1, we're wanting to multiply it by N2, right? N2. And then we'll do this plus N3. This might not be the best way to do it. Okay, but let's see. So what that gives us is you have a minimum, which is a 0.02. And so probably what we'd want here, we wanted 0.05. We would want it to be this. That's not percent times plus. That's not right. So what we actually want, so we want that plus to not be, because our integer, that this value here is like 0 to 16,384, right? Or plus or minus 16,384. So what we actually want, run it backwards. That's going to be the wrong thing. So what we're actually wanting on this is, if it runs backwards, would that work? We don't want it to have a negative set point. We want it to just have a 0 set point. So, so these are all the different things that you think about. The different kind of corner cases of like, here's what I'm going through and thinking about. So, get on the sketchpad. So we got a situation where our metering roll, we know we want our speed set point set here. So normally these are running this direction, right? So we set them up to where those are both positive. And so we always want this thing running faster than this. Like whatever this is running, we always want it to run faster in that direction because this creates tension. Well, if you go the other way and this is running backwards in the negative direction, it sets it up totally different. And so really what you're wanting to do is like add some fixed value to the speed set point, right? Instead of like a percentage, because if this is negative, you want it to be less negative, right? So if this is trying to pull it that way, you're wanting this guy, the mandrel, to actually hold back. And so you don't want to do a multiply here. You want to do some fixed value, which this is kind of getting into a point to where you'd almost just want to do like drop in a SCL line, you know, because this math has a couple of different cases, a couple of different things, but let's keep it in our let's keep it in this, and let's just step it out, because what we're wanting to do is wanting to bring in our actual speed, and eventually we're wanting to get this out, so we might have to round, and we're wanting to add to it like 3% of 16384. Let's do this. Let's do a multiply block. Put a multiply block somewhere. Again, we're just kind of stepping through the things that you have to think about, because remember, these, like if we were to look at them in real time, it's going to be something 0 to 16384. That's the number that it's going to be, and that's going to represent some sort of percentage. And so normally before, when I said you wouldn't want to convert it back and forth, I'm like, okay, we actually kind of do, because we want to generate like 16384.0. We want to generate it's fine, like a 3%. Okay. We want to generate this, and we want it to be in real. All right. We want to have that available to us. Whatever that number actually is. It's going to be some like 163 times 3, whatever that is. But so that'll be like 400 something, and we want to add that to this. So in order for that to be that multiplication needs to be in real. So this is going to be temp real. And again, what y'all can do if you're watching this on demand or in chat, see if y'all can come up with an equation, like a one-line equation, that if you know how to use SCL, how you would do this math, because there's a little bit of conversion going on. There's a little bit of all this, and it absolutely would be pretty straightforward to just drop in an SCL line, and maybe later we'll show you how to do that, because you can literally just go through and say, oh, I want to insert an SCL network, right? And then I can go in and just be like, this tag, like metering roll times this, you know, but we're not going to do that. Type that out in chat. Type that in on the in the comments of how you would do this conversion, how you would clean it up, because we're going to take this real and we want to add it to this value. So we actually need to round. So now we need to round there, and we want another temp. So we got that, and then now we want to add it to that and then move it into that. So we're going to take an add. Add. Yep. Word. That. And then, no, I deleted it. And so this is mandrel. Mandrel out. Speed set point. All right, let's look at that. Is that better? I think that's better. Obviously, we could take and know this number, what this is. But if we did it this way, we could actually set this to be like to do something like this, like mandrel data. And then do like a mandrel data dot speed. And it's going to complain about that. Second, I'm going to go back to mandrel data and then make another one here. Now it's going to like it. Right? Okay. Still not quite right, because that's going to be percent. So multiply. So let's, because that's going to come in, and the reason I'm doing this, 1, 2. I'm just multiply. So, because I want to get a number, I just essentially divided this number, the speed adder, which is going to be like, you want to add 4%. So you're going to put in 4 into your HMI. And what I did there is, instead of multiplying it by the full range, I divided that full range by 100, moved it over to, and then now that 4 times that is going to be what we have. So if we wanted 4%, we would get whatever that is, 600, right? And then that's going to get rounded out and moved, added to the actual speed from the metering roll, and then get sent over to the mandrel. Okay, so that covers our corner case too, because if it starts moving in the negative direction, that addition is going to make a less negative number, which means that the big mandrel or the roll will be less negative, right? The problem is, because that is going to be would that be a positive torque? You think that would be a positive torque, or would that be a negative torque? Let's think about that. It's moving in the negative direction, resisting the motion. So that's a generating torque, right? So that's actually going to flip over and go into a negative torque scenario, because it's trying to run slower than the other. So at that point, we would need to have a negative torque limit, right? So we can either, we can either say, hey, we're not going to allow a negative direction in running, or we are going to need to limit the negative torque, right? We're going to need to limit the negative torque to our torque limit, right? Because we're setting like some upper torque limit. So this mandrel torque set point, mandrel data.torque set point, right? So what we can do is go down here to our torque limit, right? And let's go through here. So that's the absolute. What if we did this? So that is the absolute upper. What if we now go through and take and do a multiply? Oh, Saif, welcome. Welcome, welcome, welcome. It's awesome. Hope your day wasn't too long. Yeah, this has been a long stream. We've just been kind of chatting about how to make winders, how to design them. Kind of been chilling. We're kind of going through some of the things right now about how to the corner cases. So what we've got here is we've got this upper torque limit set, and honestly, we want that set point to just be negative and then thrown into the negative torque limit, right? And so let's just take this same temp word. Actually, no, we want this output. Yeah, so let's just do this. Let's do Control C, Control V, times -1, and then put it into mandrel out, lower torque limit, right? That's how we're wanting to do this, right? Multiply auto unsigned enter. No, it's not gonna be unsigned. What you doing? It's gotta be like that. So now we've got basically whatever the upper torque limit is gonna be inverted, and is gonna be the lower torque limit. Now we just gotta make that connection back over here, right? So before we go back over there, let's make sure we know where the lower torque limit comes in. It comes in on 1, 2, 3, 4. So the fourth PZD. So let's go over to our drive, manual drive. And let's go back to torque limiting. Go down on the lower torque limit. Same thing, torque limit scaling. And now we're gonna go PZD, what was that, 2050? Yeah, PZD 2050. 1, 2, 3, 4. Okay. And then we're, again, this needs to be an this, we need to make sure that it's negative here, and we have. And that's on the fourth, double check. 1, 2, 3, 4. So lower torque limit, yep. And that's what we got. So now we actually have just covered the case to where if the metering roll, say you have a jog function and you sit there and you have a user that comes in and is like, hey, I want to run this backwards at 10 RPM or 5%, and I want to kind of unwind. We just created an unwinder. And that's where, remember when I talked about it just a second, that if you have your big roll and it's creating the tension and something else is pulling against it as hard as it can, then you have to kind of invert the logic. Well, that's exactly what we just did. We made sure that the metering roll, or sorry, the mandrel is always going to be running, no matter what. It's going to be trying to run a little bit faster. It's going to be trying to run 10% faster, or whatever this speed adder is in percent. It's always going to be trying to run that percent faster than the metering roll. And so a larger negative number, or sorry, a less negative number is going to be exactly what we need. Because if the metering roll is trying to pull harder, it's going to be holding back that torque. And so we have this situation, and that will put it into a negative torque limit, because at that point it's a generating torque. Cool thing about it though is it will essentially even out, because we have the DC link, the common DC bus. It'll essentially even out, and you'll just have your magnetizing current and the current to move kind of through all the friction, and the generating torque from, or the generating current from the what's it called, the mandrel, will just a little bit of that, all of that torque will get used up by the pulling. And yeah, so you're not going to have this like loss of heat, the extra loss of heat. So all you're going to be losing, or all you're going to be doing, is just the forces involved in pulling and creating that tension. So very efficient way of doing it. And honestly, you can do this on any drive manufacturer, any type of setup. You can even set this sort of stuff up on other PLCs, because I haven't done anything so far, or actually I haven't used anything in this that isn't on anyone else's PLC, isn't on anyone else's drive. It's just for this in particular thing. That's what we have. So yeah, if you've made it to this point, like, thank you for watching. If you've come in the middle, There's a lot of information about how to set up the terminologies that I'm kind of using, the physics behind it. We talked for about an hour before actually starting programming anything, just about what's a winder, all of this stuff. So absolutely go back, a lot of information. I know these are long. They're not intended for you to sit down and watch at one time. I can't even listen to myself for that long. So go back, put it on as you're working through stuff, just to kind of like osmosis. And you'll probably pick up on something that you hear like, oh wait, I didn't think about that. And yeah, if this was your first time that you're watching either on demand or on the stream, I'm so glad you're here. I say that multiple times through because these videos are so long. You have people that come and go. We appreciate any type of interaction, any type of community interaction that you have here, because it just grows all of you guys that are trying to work through these issues in automation. And yeah, so that's what I'm here for, trying to grow this. If you aren't subscribed, please consider subscribing. That's the best way to help this channel, is to get us out there. The more subscribers, the more YouTube puts this information, and more it understands who wants to see this type of video. And so yeah, we have gone through pretty much from start to finish the design, setting up the drives, setting up the PLC program, talking about from the core fundamentals of what you need to work with. And so this has kind of been a fun, a little laid back, but we'll probably start at some other stream from this this project, because it's kind of a project that is pretty simple at this point, pretty straightforward, but then we can kind of start adding on to it, like maybe bring in an HMI and show you how you would want to set these settings up and bring them in. Maybe bring in a position controller, how you would want to actually meter out that, because we really only talked about one thing today out of the three things that we talked about. We have our length, we have our tension, then we have cutting. The length and cutting require some sort of position control. So maybe the next time we come in, we'll add in some position control functionality one way or another, and kind of give you options on that. But yeah, so I know some of you came in late. I appreciate you tuning in for what you could. Love seeing all the international crowd. I love, yeah, I just love seeing that these problems, these issues, these solutions are universal. And yeah, it's great. The universal language of automation. So it's great to see this channel growing and this community growing. And again, I'll be going out of the country for later this week for about a week. So it'll probably be 2 weeks before I'm able to do another live stream. But if in the meantime you have questions, feel free to drop comments on any video. Building a very large library of kind of individual topics that are on edited videos. If you're not aware, there's a lot there. There's a lot of live streams. Most of them are at least 2 hours long. Not something you're going to sit down and watch at one time. But yeah, I really appreciate everything. And yeah, we've talked a lot about this, and hopefully you've gotten something out of it. And if not, I'm here. I will see you in the next one. In the meantime, just keep learning and keep trying, and yeah, keep pushing yourself wherever it is. Till then, I'll see you next time. Mm-hmm.